Okay. Yeah, thanks a lot. Okay, so yeah, I want to talk a little bit about the extension complexity. Now, what's that? Now, imagine you have a polytope, and typically in, let's say, in optimization, the way how you write a polytope it's you write it as all x that satisfy some linear system of inequalities. But you could actually also write a polytope in a different way. You could imagine that you add some extra variables y, and then you write your polytope as all x, so that there is a y, so that you satisfy some other system of linear inequalities. And now you could, so geometrically, this means you have your polytope in your original space, and you think of writing it as a projection of a polytope in some higher dimensional space. Now this would be the set of x, y that satisfy these inequalities. And you might wonder, why should you do that? The reason is that there are many examples where you need, let's say, exponentially many inequalities to represent your original polytope. But if you go to some higher dimensional space, then you need, let's say, only polynomial many inequalities. And this polytope, this higher dimensional polytope Q, this is called a linear extension of the original polytope. And so the quantity that we care about, it's the so-called extension complexity of our original polytope. This is the smallest number of inequalities that you need to describe a higher dimensional polytope Q that you can project down to recover P with a linear projection. Okay. Yeah. Okay. So in other words, you have your original kind of optimization problem, and you think of introducing some kind of auxiliary variables y, and then you want to write down your problem, let's say, as a linear program. And the question is, how large does that linear program need to be? Is this clear so far?
You want to say that also the second one has an efficient algorithm? Some sort of reduction, right?
Yes, yes. Let's say if you manage to write this down with a polynomial number of inequalities, I mean, then you can just optimize a function over that higher dimensional polytope, and that also gives you an optimum over the lower dimensional polytope. Okay. Now, there are many examples where this kind of technique actually helps to reduce the number of inequalities that you need from exponential to polynomial. And some of the examples are the spanning tree polytope. You might remember that in the original space, you need essentially for every cut, you need some inequality telling you how many edges can you take in the cut, but you can add some kind of flow variables, and then you only need n to the 3 many inequalities. And other examples contain the perfect matching polytope in planar graphs and graphs with bounded genus. And also for the permutahedron, you can get a nice, very efficient representation if you allow some extra variables. Okay, but this is actually not what I want to talk about in this talk. Here I want to care more, when is this kind of extension complexity, when is this super polynomial? When is the polytope inherently difficult, and when do you really need more than polynomially many inequalities, even if you go to a higher dimensional space? Okay, so I'm talking about lower bounds in this talk. Now, what is known for lower bounds? Well, actually, everything started with a famous paper of Yannakakis, and what he showed is that at least if you restrict yourself to what he called symmetric linear programs, then for the traveling salesman problem and for the perfect matching problem, you need exponentially large linear programs. What does symmetric mean? It's actually something intuitive. It means if you kind of rename your nodes, there must be a way to rename your variables so that you end up again with your original formulation.
It's interesting that he developed this idea trying to refute a paper claiming P equals N, that many people believed at the time.
Right. Yeah, so there was a sequence of, there was some guy who claimed that he had a big polynomial-sized linear program to solve the traveling salesman problem. Then whenever somebody came up with an argument why this is not the traveling salesman problem, then the guy added some more inequalities. And I mean, it became more and more difficult to find, let's say, a small counterexample. And then Yannakakis came up with what people usually call the best review report ever. So he kind of proved that like all these approaches cannot work because all those linear programs naturally were actually symmetric. Okay. But it turned out a couple of years later that this restriction to only look at symmetric LPs, this is actually a restriction. So there can be a superpolynomial gap between the size of symmetric LPs and non-symmetric LPs. Okay. Yeah, there's one thing that was not so difficult to prove is essentially you can use a counting argument to show that there must be some 0-1 polytope that has a high extension complexity. It's essentially the same counting argument that you use to show that there is a hard Boolean function which requires large circuits. Well, it's a little more tricky because you have to count polytopes instead of circuits, but the same basic counting argument works here as well.
A random polytope is you just take a random subset of the cube and take its convex.
Yes, exactly. Okay. Okay, so that didn't lead anywhere. But then there was the big breakthrough of Fiorini, Massar, Pukuta, Tivari, and Wolf, and they showed that essentially the theorem that Yannakakis had for the Traveling-Salesman problem, that this holds also for asymmetric LPs. So that there's no LP whatsoever of polynomial size for the Traveling-Salesman problem. And this also essentially worked for a couple of other NP-hard problems, and a couple of other polytopes that model NP-hard problems. Okay. The technique which they developed, you can essentially extend this to argue also about the approximability of certain problems. And for example, you can show that let's say a variant of the clique polytope needs you cannot even approximate that polytope with a polytope that has a small extension complexity. And there was a lot of nice work on this as well.
The approximation is in terms of the optimal value of some direction. It's not about...
Yes. Okay. And there was a completely independent line of research by Chandli, Raghavendra, and Steurer. And they showed that if you look at CSPs, for example, you can look at the max cut problem, and there you cannot have an LP that approximates the problem better than a factor of 2. So you cannot have such an LP of polynomial size. How they do that is essentially they show that if you have an integrality gap instance for the Scherali-Adams hierarchy for the problem, then you can use Fourier analysis to show that essentially no LP can do better. This is I found this particularly interesting because you know that for max cut, you can approximate the problem better than 2 using an SDP. So this gives you a strict separation of the power of SDPs and LPs, at least if you talk about approximations.
This is the best separation, no?
Between LPs? Probably, I would call this the most striking difference. If you ask the best one in terms of like the size, I would need to think a little bit about it. Actually, well, there is some spectrahedron where you can, which kind of pops up already in the original work of Fiorini and others, where you have a spectrahedron of size n essentially, and kind of any LP that approximates this well has size 2 to the n or 2 to the root n. Yeah. Well, this is a difference between polynomial and slightly superpolynomial. So.
There was an omega n round separation for the Schreiber hierarchy.
Yes, but it's not the case that the exponent is the number of rounds. So they lose a lot in their proof. Yeah. So it was one of their questions whether you could actually kind of make their reduction kind of more efficient. In principle, you should get something like 2 to the n here. That's what you would expect. Okay. Yeah, nevertheless, all the polytopes that you have here, they are NP-hard. So, okay, this is a little bit debatable here because, okay, you have a spectrohedron where you can optimize in polynomial time, but it's kind of the underlying polytope. It's the max-cut polytope, so that's an NP-hard polytope. TSB is NP-hard, and so on. So this is the point where I was wondering, so what if you have a polytope where you actually, you know how the polytope looks like, and you can optimize any linear function in polynomial time. What about those kind of polytopes? And the most prominent example is actually, for such a polytope, is actually the perfect matching polytope. Okay. And in this talk, I'm always talking about the complete graph on n nodes. And okay, you probably know what a matching is. Okay, so what is the convex hull of all perfect matchings in the complete graph? Okay, you would start writing down the obvious degree constraints. So for every node, you want to pick one incident edge. But that's not enough, because if you have only those linear constraints, then you could have for example, extreme points of this form where you have an odd cycle and you have a value of 1/2 everywhere. So essentially, you need to forbid those kind of solutions. And the way how you do that is you look at any odd cut, and then you say that, well, if you have an odd cut, then any matching must cross the odd cut at least once. So you can add some inequality saying this. This for every odd cut, you need at least one edge crossing the odd cut. And it's a classical result of Jack Edmonds that these kind of inequalities, they precisely describe the perfect matching polytope. What's also known is that you can optimize any linear function in strongly polynomial time, and there's a lot known about the phase structure of this polytope. And there's also a nice separation problem. Sorry, there's a nice separation. There's a nice way to solve the separation problem. Let me call it that way. This is, you use Gomery Q trees. Okay, so you have a lot of nice properties for the matching polytope. But if you count how many inequalities you have, that's essentially exponentially many, 2 to some constant times n, many inequalities. So you might wonder, can you add some extra variable so that you can reduce the number of inequalities that you need significantly? And yeah, that's the main result of this work, that you can't. Yeah, the only thing that you might hope for is to prove the constant that is in front of this, that is in front of the exponent. But apart from this, this is tight. Okay, no way to get anything better. And the best that was known previously was just the trivial quadratic lower bound that you get from the dimension. Okay. Yeah, but before I go more into the details, let me talk a little bit about the background of extension complexity, and there are a couple of insights and theorems that we need. The first thing that I want to discuss is the so-called slack matrix. Now imagine that you have a polytope, and imagine that on one side you have the polytope as the convex hull of some points. So this is the vertex description, and on the other side you have the description as linear inequalities. And now the slack matrix, it's a huge matrix where you have a row for every facet of the polytope, and you have a column for every vertex. And then the entry that you have in the slack matrix, it represents the slack which that vertex has with respect to the facet. Okay. Now this is it has to be a non-negative matrix by definition. And one thing which is very important in this context is the so-called non-negative rank. And the non-negative rank of a slack matrix, it's the smallest number of columns of a matrix U and rows of a matrix V, so that you can factor your matrix as U times V. And the important thing is that these both factors, U and V, they have to be non-negative. So if you remember what's the usual rank that you know from linear algebra, there you would not require that the factors are non-negative. So this is, yeah. So this is the variant of the usual rank, and this is at least, obviously, at least as large as the usual rank. Okay. Now, where's the connection between this, these slack matrices on one side and then the negative rank and the extension complexity of a polytope? It's the theorem of Yannakakis, which says that whatever polytope you have, you can take any slack matrix, and then the extension complexity of the polytope is exactly the non-negative rank of the slack matrix. Okay, are you interested in a 2-minute proof, or do you? Okay, okay. I'll just wave my hands a little bit and give you an outline of the proof, which is not very difficult, actually. Okay. So you need to prove two things. First of all, the easy direction is if you have a factorization of the slack matrix, why does it give you an extended formulation? Well, you can just write your polytope as all x so that there is a y, which is not negative, and then ax plus this factor times y equals the right-hand side. Why does that make sense? Because, okay, imagine you have a vertex of the polytope and you want to find a y so that you can satisfy this equation. Which y would you choose? Well, you want that ax, and then you need to add the slack which this vertex has, so that you make this an equation. And the slack, okay, let's go back to the slack matrix. So for a vertex here, you would just use this column of v. You would use this as y, and then if you multiply this out, you get exactly the slack, because this is how the slack matrix is defined. Okay. Okay. Now this is the reason why this is actually this is an extended formulation of your original polytope. Okay, and it has the right size. Now this is somewhat the more complicated direction, and this is actually the one that we need for our theorem. This is that if you have an extended formulation, why does it also give you a nice factorization of the slack matrix? Okay. Now let's assume that this is our linear extension, and okay, I was talking about this linear projection, and let's just assume without loss of generality that the linear projection is the projection on the x variables. Okay. Okay. In other words, whenever you have a point in your polytope P, you can look up and you are going to see a point in Q. Okay. Now, how do you get this, the factorization? Well, what you need is for every facet of your polytope, you need a non-negative vector of small dimension, and for every vertex, you need a non-negative vector of small dimension, so that their scalar product gives you the slack. It gives you the slack which this point has with respect to the facet. Okay. Now, how do you choose those vectors for the vertex and for the facet? Well, you know by LP duality that you can write this inequality, this facet-defining inequality, you can write it as a conic combination of inequalities of your higher dimensional polytope Q. And we take the vector, the U vector, as the vector of the conic combinations that you need. Okay.
So you want to prove that it's non-negative?
That it is a conic combination, so that is non-negative. Now, if you remember LP duality, it essentially says that whenever you have a feasible inequality, you have an inequality that's feasible for a polytope, then you can add up some original inequalities of your polytope, and you only need non-negative multiples, and then you get your original inequality. This is essentially what we're using here. Okay. And for your vertex, what you're doing is you look up into the higher dimensional polytope, and there is some point that projects down to your vertex, and then you take the vector of slacks which this point has with respect to the facets of that higher dimensional polytope. When this is the vector of slacks, so this has to be non-negative by definition. Okay, and then you just calculate what is the scalar product of those two vectors, and then if you do the calculation, then you see that you recover precisely the slack that you need. The intuition is that geometrically, you want to get the slack of this point with respect to this facet. Now, it's kind of, you look up into that higher dimensional polytope, and now you know that this slack, it's essentially, it's a mixture, it's a conic combination of the slack that this point has with respect to those inequalities. So I hope this is kind of a bit intuitive. Okay. Are there any questions? Okay. Okay, so this is the theorem of Yannakakis from the beginning of the 90s. And what it shows is that it suffices to give a lower bound on the non-negative rank of the slack matrix. Okay. And one way how you can in principle get a lower bound on the non-negative rank of any matrix that is non-negative is using the rectangle covering lower bound that you essentially know from communication complexity. Okay, let me briefly remind you what it means. Let's say you have a non-negative matrix and you have a non-negative factorization of that matrix. Then you could imagine that you forget which numbers you actually have in that matrix, and you just check, is the number positive or is it 0? And then you can see that if you take a column of your first factor and you take a row of your second factor, the corresponding row of the second factor, they actually induce a combinatorial rectangle in your slack matrix. And in this rectangle, all the entries must be strictly positive. And if you look at all the rows and columns, then you get a covering of precisely the positive entries in your slack matrix. Okay. Now, in other words, if you know that you need at least R many rectangles to cover precisely the positive entries in a slack matrix, then this gives you a lower bound on the non-negative rank of the matrix. Okay. So the first obvious idea would be, if you want a lower bound for the perfect matching polytope, look at the slack matrix. What's the rectangle covering lower bound for that? Okay. So let's do that. And yeah, let's see why we fail. Okay. Yeah, so the slack matrix of the perfect matching polytope, we have a couple of different inequalities. We have the rank, the degree constraints, and then we have non-negativity, and then we have these odd-cut inequalities. But actually, only the odd-cut inequalities are exponentially many. The others are only linear and quadratically many. So we can actually completely focus our attention to the part of the slack matrix that comes only from the odd-cut inequalities. Okay. So let's look at the slack matrix, which is defined by this. So for every matching and every odd cut, the slack which this cut has with respect to that matching, it's the number of edges that they share minus 1. This is precisely the slack. Okay. Now let me argue why you can cover this slack matrix with only n to the 4 many rectangles. And this was actually already observed by Yannakakis himself. Okay. And yeah, the rectangle covering is quite easy. You take any pair of non-incident edges, E1 and E2, and then you define the rectangle in the sense that you add all the cuts which cut both of the edges, and then you add all the matchings that contain both of the edges. And then you know that if you look at the intersection of that odd cut with a matching, then you're going to have at least those two edges in the intersection, so you're going to have a positive slack. On the other hand, any entry UM where you do have a positive slack, you must have at least two edges, so it's going to be in one of those rectangles. Okay. Good. If you have a little bit of a closer look, then if you have an entry of a cut and a matching where you share precisely k edges, then this entry is in precisely k choose 2 many rectangles. And this is a positive number if k is at least 2. Okay. Now let's be a little bit naive. So if this is an upper bound on a lower bound, so this doesn't give us anything. But if we're naive and we try to use this rectangle covering to get a factorization, then why does that not work? So in other words, let's try to write our slack matrix as the sum of all the rectangles that we have. And actually, I'm a little bit confusing things here. So a rectangle, well, it's essentially, it's a 0, 1, rank 1 matrix, and it's also the Cartesian product of a set of cuts and a set of matchings. I hope you're fine with that. Okay. Now, if we take these into the form many rectangles and we try to sum them up, and we try to get the slack matrix, why does that not work? Well, obviously, it won't work, because otherwise the title of this talk would be different.
The numbers will be too big.
Yes, precisely. So if you look at an entry in the slack matrix where you have k edges that you share, then the entry that you expect in the slack matrix would be k minus 1. On the other hand, so this would be the number k minus 1 that you expect on the left-hand side. On the right-hand side, the number that you get is around k squared, because that entry is going to be in a quadratic number of rectangles. Okay. Now, we do have some freedom to get a non-negative factorization. We could put some non-negative scalars here in front, but I mean, you might believe that there's no way to kind of scale this curve so that they coincide. So yeah, so that doesn't seem to work. So the question that is a little bit naive actually is, maybe whenever you have a rectangle covering, let's say with polynomially many rectangles, maybe then always these entries where you have a large slack, maybe they're always overcovered. Because if we go back, if you have an entry and you have a slack of roughly k, you expect a slack of roughly k, and then you cover that entry a quadratic number of times. So maybe this is an effect that you have in generality. And the surprising thing is actually that this naive intuition turns out to be true. This is precisely true. Okay. Good. But okay, so if we want to prove this, then we need some kind of other lower bound technique, because the rectangle covering lower bound does not work. So we need some other kind of technique in order to apply this idea. And the technique that we're going to use is the so-called hyperplane separation lower bound. So that was observed by Fiorini, that in principle one could use this, though he didn't have an application for that at the time that he found it. Okay. Now let's say, okay. Now what we want to do is, let's take a matrix W, which has the same dimension as our slack matrix, and we want to consider this matrix W as a linear function. It's a linear function on the slack matrix and all the matrices that have the same format. And let's say that we can show that all the rectangles that have the same format as the slack matrix, they have a small value for that linear function. Let's say the value is at most alpha.
What do you mean they have the same format as the slack matrix? They are just rectangles in the slack matrix.
Yes, if you want to say so. Okay,
you just take the characteristic vector of rectangles, well, they are all positive.
Yes. Okay.
So these R's are just 0, 1.
Yes. Okay. So essentially this says that if you, for all 0, 1, rank 1 measures, you have this inequality, and you want that your alpha is small so that you get a good bound. Geometrically, you can imagine that you have some high dimensional space, and you have a point for every of your rectangles, and then it essentially means that it lies on the left-hand side of some hyperplane that is defined by the matrix W. Okay. The second part that we need is that we want that the linear function, while it is small on every rectangle, we want that it is large on the slack matrix. And then one can argue that then the non-negative rank of the matrix S must be large. It's essentially the fraction between the value which S has on the linear function divided by the best value of a rectangle on that linear function. Why is that the case? Well, it's actually not so difficult to prove because you can imagine that okay, if you would imagine that your slack matrix is the sum of rectangles, then this would be clear because you have a linear function, it's large on the slack matrix, and it's small on every of your summons, then you must have a lot of summons. Okay. Now, it's not that easy because a slack matrix, it's not the sum of rectangles, it's the sum of arbitrary rank 1 matrices. Okay. Okay, but the first thing that you can observe is that if you scale your rank 1 matrix so that the entries are between 0 and 1, then the convex hull of those matrices is precisely the convex hull of the rectangles. Or in other words, whatever rank 1 matrix you give me, let's say the entries are between 0 and 1, I can write it as a convex combination of rectangles. And that means that whatever linear inequality I satisfy for all rectangles also holds for all rank 1 matrices where the entries are between 0 and 1. Okay. And now you can just imagine that instead of having the sum of arbitrary rank 1 matrices, you just scale them a little bit so that they fall into this. And then you get the claim. This is just a one-line calculation.
Yeah, but you get S or you get a scaled version?
There is a scaled version, but you need to scale it only by the biggest entry in the slack matrix, which for matching it's n, and we're heading for an exponential bound, so this is something you can ignore. Okay. Any question concerning this? Okay. Okay, so we want to use this technique to show a lower bound for the perfect matching polytope. And now the obvious question is, how should you choose this magic linear function W? And now we have that intuition that it seems that whenever you have a rectangle covering, you're covering too many of those entries that have a large slack. So we want to define W so that it exploits this inside. Okay. And okay, let's see how that could go. Okay, let me remind you that this is our slack matrix, and let's introduce a little bit of notation. Let's say QL. This is the set of entries in the matrix where we have slack L minus 1, and it means that we have an odd cut U and a matching M that share precisely L edges. Okay. Now then, my magic linear function W, it's defined so that whenever you have a slack 0 entry, you put a value which is minus infinity. Let me convince you that this makes sense. What we want is that this linear function W, it has a large value on the slack matrix while it has a small value on all the rectangles. Now, if you have an entry where the slack matrix has a value of 0, then you would want to make the corresponding entry in W as large as possible, because you hope that, I mean, it doesn't harm here, and you hope that it kind of kills a couple of rectangles here. So did I say as large as possible? Sorry, as small as possible. Yes.
So this
yeah.
is for free.
This is for free.
And that's what
Yes, yes, yes. Okay. Okay. Now, okay. Now let's say that okay, for every this is the smallest positive slack, which is a slack of 2. It's when you have 3 edges intersecting. This is for parity reasons. This is the smallest possible positive slack. And there, let's say we take a measure of 1 and we distribute it evenly over those entries. Okay. So far, essentially, this looks like a rectangle covering lower bound. Yeah, but we have a little bit of space left for, and let's see what we could put into there. And there we take some large constant k, 501 works, if you like. Okay, initially in my paper I had let's choose a large enough odd constant, let's say 500. And after a while I discovered it's not so odd as I would like it to be. Yeah, okay, let's say 501. Okay. And now we again take a measure, and we put the minus there. And we just scale a little bit down, because we know that, okay, if you have k edges in the intersection, then you have a slack of k minus 1. So essentially, this is multiplied with k minus 1, and I want that this cancels out.
These numbers are easy to calculate the QLs because of symmetry.
Actually, I never even calculated how many entries are in there. We will talk about the probabilities and the measure in a couple of minutes.
Anyway, it's a symmetric.
It is a symmetric thing, so you could, though you have matchings, and if you want to, okay, there's some formula how many matchings you have in some graph. Okay, but you can. It's a complete graph, so that is doable. Yeah. Okay, but actually we never needed that. Okay, good. Now you can calculate what is the value which this linear function has on the slack matrix, and then you see that the numbers are cooked up so that you get a constant that is not even too complicated. It's it's at least 1. Okay. So obviously, what we want to show is that any rectangle can only get a tiny value here. Okay. And in fact, what we can prove is that if we take the constant k large enough, then whatever rectangle you have and you multiply it with a linear function, you can only get something that is exponentially small. And then you plug in this value here, and then you get that the non-negative rank must be exponentially large. Okay. Good. So this innocently looking lemma is the thing that we need to prove for the next I don't know, like 30 minutes or so, or yeah. Okay, but this is actually the hard part to prove. Okay. Good. Let me introduce a little bit more of notation. I want to talk more about measures than instead of how many entries you have. So let me call the Lth measure of a rectangle. This is just the number of entries. This is the number of entries where you share precisely L edges divided by the total number of entries where you and M share precisely L entries. So this is just the corresponding measure. And actually, I can rephrase this lemma in the following way. I can rephrase this as follows. Whenever you have a rectangle and you don't have any pair UM that shares only one edge, if this is the case, then you can show that the fraction of entries in the rectangle of where you share 3 edges, this is much less than the fraction where you share k edges. And this decreases by a quadratic factor in k. And then there is some exponential error term, exponentially small error term.
So again, these are rectangles where the slack is 0.
Yeah, you have a rectangle and you do not have a single slack 0 entries. Then the point is that the consequence of this is that this changes how the measures can look like. Assume you wouldn't have this, then you can just throw in imagine you throw in a random subset of matching, then a random subset of cuts, then in expectation those measures would be the same. So you wouldn't know anything. But as soon as you know that you're not having any like 0 entries, it dramatically changes how the measures can relate to each other.
That's why precisely the rectangles you look at, those with slacks which don't.
Precisely, yeah.
Which have positive slacks.
Yeah, these are the only ones for which I need to prove something, because if you have a rectangle and you have a single entry where the slack is positive, then you multiply this with minus infinity and you're out of the game. So, okay. Let me try to convince you why this lemma implies the one on the last slide, namely this one. Now let's say, how would you like to get this large? You definitely cannot include any slack 0 entry in your slack matrix. And then you want to include as many of those entries as possible, but you know that the fraction of these entries, it's quadratically larger in k, if you forget the error term. So whatever you gain here, you lose much less here. So, okay. So the only thing that you could possibly get is that exponentially small error term. And yeah, that's
so
it.
Do you really need the quadratic 1/k squared, or anything superlinear would be good enough?
Anything superlinear would be fine, yes, yes. Okay. Okay. Good. Okay, this is kind of not a very good visualization. So you have these. Okay, you have a rectangle in your sitting in a slack matrix, and you know that you don't have any slack 0 entry, and then you want to argue like how many of those entries can I cover, and then it kind of turns out that well, you must have much more of those entries sitting in your rectangle. Yeah. Okay. Okay. This visualization is not very helpful, I'm afraid. Okay. But okay. Now, what is the actual technique that we're going to use to show this inequality? And this is a technique that was already developed by Sasha Rasborov in the context of communication complexity. So this is usually called the rectangle corruption lemma. And okay, so if you know it, what comes now might look a little familiar to you. Okay. Now, essentially what Rasborov would do in this case would be the following. So you have a big matrix, and you want to show that some inequality holds for a rectangle. Then you imagine that you take a second kind of, let's call this a partition rectangle, which is, you take this at random, and then you check whether the inequality at least holds if you restrict your attention to the intersection with this rectangle. And these kind of rectangles, they are nicer structured. So you have some nice structure here, so it's kind of easier to show it here than in general. Like, this is a very high-level picture. I'll try to be more precise in a little bit. Okay. Okay, so the first thing that I should probably do is define how this kind of partition rectangle should look like in this context of matchings. Okay. Now now let's imagine that our partition looks as follows. We have a subset of nodes in our complete graph. Let's call that A. We have a subset of disjoint nodes. Let's call that B. And then we have subsets C and D. And they have a very particular size. I'll say a little bit about it in a moment. And okay, now the nodes A, they are partitioned into blocks that have a very particular size. And also B is partitioned into blocks, also having some particular size. And okay, now we're not looking at all the edges in the complete graph. We're only looking at those edges that are only running inside the blocks, or that are running between these middle parts C and D, or inside C or inside D. Okay. Now, this is definitely not very intuitive, but a little bit of intuition would be that this is a highly symmetric object, in the sense that if you delete 3 nodes from D, then the rest that you have looks like any of these blocks. If you delete 3 nodes from C and from D, then the rest that you have here looks precisely like one of these blocks. So we have a lot of symmetry, and this is something that we're going to use later. Okay?
In the case of Rasborov, this was for the disjointness matrix, it was just pairs of subsets of size, I don't know, some constant times n, which are either disjoint or intersect.
Yes, yes. And his partition would be much easier. Here he would have just one element. This would be just one index. And here the blocks would be also just one element, which also is nicely symmetric. So we need to work a little bit more to get kind of the same type of symmetry. Okay. Okay, good. Okay, so this is actually this is a constant, right? So we have a constant number of nodes here, and we have a constant number of nodes in each of those blocks. So we have a linear number of blocks in total. This is important. Okay. Now, I should, yeah. To define what kind of rectangle this partition defines, I need to tell you what are the matchings that lie in the partition and what are the cuts that correspond to the partition. And the set of matchings are just the matchings that you can form with the edges that you see here. And the cuts that you have in the partition rectangle, they're just the cuts that you can form by taking some nodes from C and then any set of blocks from the A part, but I require that the cut does not cut any of the block. So it has to either include the complete block or not include any of the nodes. Okay. Now, why should I do that? If you look at a matching and a cut that corresponds to the partition, then you see that where can they intersect? They can only have intersection here, right? And we have only a constant number of nodes here and a constant number of edges. So we only have a constant area where the cut and the matching can actually intersect. And this helps us a lot in order to control their intersection patterns.
So can you say again which cuts you allow in T? So partition T is not yet a rectangle. You have to tell us what are the matchings there and what are the cuts there. You told us what are the matchings.
Yes.
Yeah. What are the cuts again?
The cuts are take any nodes in C and then take any subset of the blocks. But you have to take either put all of the blocks into your cut or none of the vertices in the block. So you can only take complete blocks. This is the family of cuts that corresponds to the partition. Okay, good. If it helps you, then what Rasborov did is that he had a subset on one side and a subset on the other side, and then he allowed that they only intersect in this middle part. Yeah, and this is kind of what we're trying to simulate that. Okay. Any other questions? Okay. Good. The next thing is that I would like to rewrite my measures so that I'm using this partition notion. In other words, okay, now there is this measure 3. So this is an entry. Essentially, we take a random entry of a cut and a matching where they share precisely 3 edges, and then we need to check does this lie in the rectangle. So let's imagine one of those green entries, and we check is it in the rectangle or not. And we do this now in 2 phases. So first, imagine that you take a random partition, and then you take a random entry UM where they share 3 edges in the partition, and then you check does it end up in the rectangle.
So, but the family of partitions is symmetric, so that this gives a uniform.
Precisely, yes. Okay. Now, okay, so what we are doing is, okay, the first step is we take a random partition. This means uniformly at random. So you take uniformly your blocks here, then in the rest you take C, and the rest you take D, and so on. Okay, this is a uniform thing. And then in the partition, okay, how do you get an entry where you share, how do you get a cut? How can you find a cut and a matching where they share precisely 3 edges? Well, let's just fix those 3 edges so that they're running between C and D, because we know that all the intersection can only go on there. And then we just pick a matching containing these 3 edges, and then we take a cut, which cut precisely these 3 edges. And then we can be sure that we have a pair UM, and they intersect precisely in those 3 edges. Okay.
You could have taken any subset of the blocks on the left, and it would still cut these 3 edges, right?
Yeah, you only make sure that your cut it contains these three guys, and then any subset of blocks. But since it contains complete blocks, you're sure that there's no intersection with the matching here.
Yeah, I just was pointing out the cut is not uniquely defined. It's even given H. Right? Given H, it just tells you which three vertices in C to take. But you can do now, I mean, there are lots of cuts that are consistent.
Yes, yes. Sure. Okay. By the way, so once we have fixed those three edges and we have fixed the partition, actually the choice of the matching and the choice of the cut is independent. So that actually simplifies the calculation of the probability a lot. Okay. Good. Okay, so this is how we generate this three measure. And it probably comes to no surprise that you can also generate the other measure in a similar way. So we want to find an odd-cut U and a matching M so that they share precisely k edges. And we again can do that by taking random partition. Then we randomly take k edges that run between C and D. Then we take a random matching which extend those k edges. And then we take a random cut which cuts precisely those edges here. Okay, good. And the good thing is that we can kind of better compare those measures because they both correspond to a partition. Okay, good. Okay, yeah. Before we go on with this, let's for a couple of minutes forget everything that I told you about matchings and cuts and so on. And yeah. If you look at the matching, then this is going to be uniform one.
Doesn't it have some constraints on like the size of the things based on what jumped into that block, like the sort of shaded rectangle that you have representing the cut? It's either going to have those over.
Okay. I'm generating a uniform cut of a certain size, so they will always have a certain size.
I see.
Yes. Which is linear in the number of nodes. Okay. Okay, thanks. Yeah. Okay, yeah, what I want to talk about a bit is it's essentially if you have...
Can you go back to the previous one?
Sure.
Why is the cut linear in the size of the... What is M in this? That's also linear?
This is like the number of nodes divided by 500, divided by k, essentially. Okay. Yeah. Okay, now let's imagine that we have some vectors. So we are away from matchings and cuts and so on. And let's imagine that we have a set of vectors, and let's say the vector is n-dimensional, and the entries are between 1 and q, and imagine that q is some constant. And you can imagine q is 2 if you like, so it already makes sense there. Okay, so you have a big set of vectors, and let's look at a random experiment. Let's say we take a random vector from that big set of vectors. And let's say we look at the coordinate in that random vector, in the vector, and we see what the random experiment gives there. So maybe the first vector gives you this value, the second one this value, and so on. And what I claim is that if the set of your vectors is large enough, then the distribution that you're going to see here is going to be close to the uniform distribution. Well, at least for most indices. Okay, a little bit more formally, let's say you have an epsilon n fraction of indices where the distribution that you're seeing is an epsilon away from a uniform distribution, however you want to define that. Then the fraction of vectors that you could have, the density can only be exponentially small. Okay, so this is an insight that was already used by Rothvoss. Okay.
Just an entropy.
Yes. Okay. So I guess a couple of you know it already, but it's a one-line proof. So let me just sketch it. So how would you show this? Okay. Now, what is the entropy of that random variable? Well, it's just the size of the set where you're picking the guy from. Sorry, it's the logarithm of the size. Okay. Now, okay, well, it's the entropy of a random variable, so you can write it by summing over the entropy of the different coordinates of the random variable. And now let's assume that you sorry, that you have a lot of variables. You have a lot of coordinates where the distribution is not the uniform distribution. So let's say it's kind of biased. Then you know that the entropy here must be a little less than the entropy of the uniform distribution. If you want a picture for q equals 2, so imagine you have a coin, and with probability p you get tail, and with probability 1 minus p you get head. And so what is the entropy? Well, you certainly remember that the entropy it's maximized if you have a fair coin, and then the entropy is it's the logarithm of 2. And if you're a little bit away from the uniform distribution, then the entropy is a little less. It's kind of obvious in this case. It's not so hard to make a calculation so that you see this is true in general. So whenever you have a random variable, it's a little bit away from the uniform distribution, then the entropy is a little less than the entropy of the uniform distribution. Okay, and it means that you have a linear number of entries where it's kind of you save a small constant in the entropy, then the total entropy that you get, you lack a linear number of entropy. You lack a linear amount of entropy, and then you just rearrange, and then you get this inequality. Okay?
Rothvoss is that 99% are unbiased.
Yes. Okay. And well, we can actually rephrase this, and we can say the following, that if you have a large enough set, then for most indices the following is true. You can look at a different random experiment where you take the x now uniform from the set of all vectors, all possible vectors, and then you test, is it in x? So essentially you test how dense is x in the set of all possible vectors. And then you know that if this was an unbiased coordinate, then you get essentially the same answer as if additionally you condition that the coordinate has some value, j. Okay. So in other words, you have some kind of a density test, and you can condition on some local variable, and it's not going to change the answer of the test. And this is essentially our business model, because this is what we're trying to do. We want to see how dense is a rectangle, how dense are the matchings in the rectangle. And now this says that, for example, instead of looking at a random matching, we can condition that, look, these kind of edges, they should be included in the matching, or they should be excluded in the matching. And this is not going to change the answer. Okay?
For this, it's important that you care only about constant size.
Yes. We will only condition on, let's say, like a constant size events. Okay. Good. So let's come up with a definition for matchings and partitions. And if you remember the Rasburg proof, then he had some notion what a good partition is. And let's do the same here. So let's look at the partition, and let's look at 3 of those edges. And let's call this pair good with respect to the matching part if the following is true. Let's imagine you take a random matching out of the set of matchings that correspond to your partition and that extend those 3 edges. And let's look at this part. And now let's take this random matching. And what I want is that what I see here is a uniform random matching. And I know that essentially if I take a generic random partition, this is going to be a uniform random matching. Okay. And if this is the case, so if I see here the uniform distribution, then I call this, then this is a good pair. It's a good, the pair of partition and matching, it's a good one. Okay. So how much time do I have? I need probably 15 minutes if I want a decent finish.
Okay.
Is that okay? Okay. 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 Good. And I can come up with a similar definition for cuts. So you can call the partition, the pair of partition and those three edges. You can call it good with respect to the cut part if the following is true. If imagine you extend those three nodes to a cut, then half of the cuts are going to contain only those three guys, and the other half of the cuts, they are going to contain precisely like everything here. Okay. So essentially it means that, yeah, I also have the uniform distribution here. Okay. Good. Okay. Now, this is the measure that I want to bound. I want to show that this is at most something. So let's rewrite this. And we already discussed that we can split this so that, okay, you first take a partition, and then you take those three edges, and then you check, is the extension going to be in my rectangle? Okay. And now we can split this, and so that we look at partitions that are good, we look at those that are bad because the matching part went wrong, and we look at those that where the cut part went wrong. And we know that every pair here is in at least one of those categories, so it actually suffices to separately bound each of the parts. And okay, maybe for the moment you believe me that bounding these two parts, that's a little technical, so one has to be a little careful, but it is only kind of more or less a technicality. So the interesting stuff is going on in this case, because this is essentially the generic case. It's like 99% of the cases we will be here. So I think we should talk about this case. Okay. Because this might be the surprising one. It shows that if you have a generic partition, then the contribution to the measure, to this 3 measure, is much less than the contribution to the k measure. And this is this is essentially the key argument why the perfect matching polytope does not have a compact formulation. So okay, let's talk about that. Okay. And that is this slide. So okay, let's imagine we fix a partition, and let's say we fix k edges that are running between the C and the D part. And I claim that the contribution of this partition with respect to the k measure is much larger than with respect to the 3 measure. Okay. Okay, so what are we doing? We're checking what's the probability that if we're extending those k nodes to cuts, and we're extending those edges to matching, okay, what's the probability that this is in our rectangle? Okay, that's some probability. And we want to compare this to the contribution that we get to the 3 measure. Okay. And in order to be able to compare the contributions that we have to both measures, let's say we take those 3 edges, and we take 3 of them at random, and then we see what we get. What's the probability that an extension of those 3 edges is going to be in our rectangle? And actually, we only need to account for them if they are good with respect to our definition. And good means it's good. They are good. They satisfy both definitions of goodness. Okay. And okay. The important thing is that if we have a good pair, then it doesn't matter what you condition on here. If you condition on only that you contain only those edges, or you contain like all of them, it doesn't actually matter up to an epsilon factor. So we can just we can essentially replace the h with f. So actually, the only thing that we need to argue about is out of those k edges here, if we take a random triple, what's the chance that this is going to satisfy the goodness definition? And I claim that the fraction is very small, and this is the 1 over k squared factor that we need. Okay. So I claim that this is the crucial part. That okay, you fix a partition, you fix k edges, you take 3 of them at random, And the chance that this is going to satisfy the goodness definition is actually very small.
The goodness by definition of matching.
Of both. Yeah. Both definitions. Okay. In particular, what I'm claiming is that if you fix a partition T and you look at H and H star and they are both good together with the same partition, then we must have that they intersect in two edges. And if you remember back the beginning of the talk, then we had the rectangle, we saw where the rectangle covering lower bound fails, and the construction where there was, you take two non-incident edges and you take all the matchings containing the edges and you take all the cuts, cutting those two edges. And this says that, well, this is essentially the only thing that is reasonable to do. And if you do anything else, then you're going to fail. Okay. Okay. Now, why is this the case? Now, let's suppose that you have three edges H and H star, and they both satisfy the goodness definition. And they only intersect in one or less edges. Okay. Now, okay. So if these three edges satisfy the goodness definition, it means that whatever matching I add here, I can extend it to a matching that lies in my rectangle. Because in particular, the matching is going to have a positive probability. Okay. So then I can define a matching which connects the two nodes that are in H star and that are not in H. Okay. On the other hand, also H star satisfies the goodness definition. So there is a cut which contains these three nodes, like this cut. But now, if you look at the matching that we just found in our rectangle, and you look at the cut that we just found in our rectangle, then they only intersect in one edge. And that's impossible, because we don't have any slack zero entry. That's a contradiction. Okay. Okay. Now, in other words, we just proved that if you look at the generic partition and the generic triple H, then the contribution that you get to this measure is about a 1 over k square factor of what you get as contribution to the other.
This is because the family within every pair intersects in 2 is 1 over k squared.
Yeah, yeah. Okay. And okay. Okay, in the remaining 3 minutes or so, I can talk a little bit about the technicality, just the intuition, the intuitive idea. Or do you have any question? Okay. Okay, let me argue why there's actually a small probability that a partition and a triple H it's going to be bad with respect to the M part. Well, this isn't okay. Okay. Let's see. Okay. Actually, something stronger is true. I can fix a lot of stuff, and still the probability will be only epsilon that the partition is going to be bad. So what I allow you to fix as an adversary are the following things. You can fix the three edges. You can fix all the blocks in the A part, and you can already fix essentially the blocks B, but let's say you can also fix how you would cut those blocks into half. Okay. So you can fix everything until this point. You know, the only randomness that I require so that this is true is I pick one of those blocks at random, let's say this one, and then I make this the missing part that I need for C and D. Okay. Good. Now this is the only randomness that I need. Okay. And now, why am I probably going to see a uniform distribution here? Now let's say that you have a lot of matchings that lie in these edges. Then we know that we're going to see a uniform distribution on most of these blocks. So what we're going to see here is probably very close to uniform matching. So if you take one of those blocks at random, then you're very likely that you see a uniform matching there. So you're very likely that you satisfy this. Okay. Okay, yeah, that's essentially the idea. Okay, and
For the cut, you do the same with the left side.
yes. Okay. Essentially, we have to do twice the work than Rasborov because he had sets on one side and sets on the other side. We have cuts and matching, so we need to work a little more, but okay. Anyway, so this is the end of the talk, essentially. And one of my favorite open problems at the moment is whether you can show similar lower bounds on the extension complexity of SDPs. And there is essentially nothing known apart from the counting argument. So the counting argument also works for SDPs, but there's no lower bound whatsoever on the SDP extension complexity of whatever polytope. Pick whatever concrete polytope you like and show it needs to have a super polynomial SDP representation. That would be awesome. Yeah, thank you.